In this video, we're going to talk about the area of infinitely many rectangles, otherwise known as Riemann sums. So by the end of this lesson, you should be able to answer the following little question: how is the integral defined conceptually? And by the end of Unit 4, you should be able to answer the following big question: how do we find the areas of weird shapes and then make it easier? So this unit's a bit different than the other 3 units that we've done. So the other 3 units were basically building up to the derivative and then solving derivatives and then applications of derivatives. Now we're starting a completely different topic called integrals. So for the warm-up, I want you to just think about what you did in recitation previously. If you weren't there, what we did was we looked at 3 blobs that look something like this, and we asked, how can we find the area? So people did a lot of different things. What a lot of groups found was that the smaller the object that they used to find the area, so smaller object, made it more exact, so more exact answer. And the general idea was to divide the shape up into shapes that people were familiar with. So like circles, squares, rectangles, triangles, anything like that. So that was the gist of it. But conceptually, that activity is really going to prepare you well for today. So the area under a curve is the area between a curve and the x-axis. So in this picture right here, it would look something like that area. Maybe I should do that with a highlighter. So the area under this curve would be this. Okay? To motivate why we would want to find the area under a curve, consider a speeding car with a graph of its velocity with respect to time. So we've got our speeding car on the left, and we've got our graph on the right. Okay, and we're going to keep talking about this. So when the car moves for a short amount of time, we can find its distance by multiplying velocity by time. So that's a formula you've probably seen for a while. So d equals rt is another way to see that. So we have distance is velocity times time. However, we were given the velocity graph. So if we think about what velocity times time means on the graph, you might notice that, well, velocity is a y value and time is an x value. So if we multiply velocity times time, that's actually giving us a rectangle, or the area of a rectangle. So if velocity is the height and time is the width, then we literally get the area of a rectangle, which is height times width. Okay? So if we keep doing this, if we do this for a bunch of little time intervals, then we get like this area broken up into a bunch of rectangles. And what that allows us to do is actually estimate the area under a curve. So notice we went from that first rectangle, so we went from one rectangle to a bunch of rectangles, okay? And we're not going to talk quite yet about how we get the height of each of those, but the idea is if we can use a bunch of rectangles, well, now we have this thing where the distance we've accumulated, so the car is going some distance, but actually that's equivalent to the area under the velocity curve, right? So distance and area are actually related through this process of approximations. So the process of estimating the area under a curve using rectangles of equal width is called a Riemann sum. And we're going to see 3 different types. We could use left endpoints, right endpoints, or midpoints. So like I was saying in the previous picture, we haven't quite yet talked about how we get the heights of the rectangles, but this one is an example of left endpoints. So notice that like each of the rectangles where it crosses the curve is on that left corner of the rectangle. So that would be left endpoints. Right endpoints would be the right of the rectangle, and midpoints would be the middle of the rectangle. Okay, but I just want to point out that, again, these are approximations. These are not exact answers, so that's where this is really handy as well. So notice that the error is that little piece. There we go. The error is that little piece right here that goes above the curve. Or you could also have a type of error that goes below the curve depending on what rectangles you choose. So you'll see some questions like that where it asks you, is this an overestimate, an underestimate? And that's kind of what you're looking for, is the area that's extra or less than the curve. Okay, so we know what a Riemann sum is. So what I would like you to do is take some time, do the exploring Riemann sums activity. I'm not going to do it in this video, but it's a really, so like I didn't make this GeoGebra activity, so it is really, really, really good, okay? And I think it'll give you a really good idea of what Riemann sums look like visually. So that's really important. So make sure you get that done. But the idea is we're going to end up adding a bunch of rectangles, like actually an infinite number of rectangles. And you can probably imagine that adding up this many rectangles results in a really long sum. So before we jump into any examples, I want to help us make writing a bunch of things added together shorter. So for this, we use what we call sigma notation. Okay, now sigma notation, it looks a little scary when you first see it. So this is it. Let's go back to yellow. So we've got this big scary Greek letter with some bounds and a function, and we read this, the sum of x sub I, as I ranges from 1 to n. So the big sigma means sum. The bounds on the sigma tell us how many terms we have, basically, and the function is basically a formula that we plug our bounds into, and that gives us the full sum. So it's actually really nice once you get used to using it. So as a small example, let's write the sum cosine of 1 plus cosine of 2 plus cosine of 3 dot 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 all the way up to cosine of 50 using summation notation. So first I want to point out that the way this sum is written is not super nice. So the dot 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 means fill in with your brain. So we actually have 50 terms here, but we can't see them all because it would be too long to write out. So that's where sigma notation is actually really nice. It allows us to encapsulate all 50 terms in a very compact way. So what we're going to do is we're going to first write our sigma, and we're going to decide what our bounds should be. So I'm noticing the thing that's changing in this sum is the thing that's plugged into cosine. And we start at 1 and we end at 50, so I'm going to make that my bounds. So I equals 1 to 50, and now I need to write a formula for each of my terms so that when I plug in the numbers 1 through 50, I get this exact sum. Okay, so this one's not so bad. So I notice the thing changing is the thing inside of cosine, so I'm going to write this as cosine I. And so if we were to think about writing out each term of that sum with the value of I plugged in, we would get the numbers 1 through 50 inside of cosine. So that's exactly what I want. So notice how much nicer this is than the original way we wrote the summation is. So that's a whole lot nicer, and that makes us happy. Okay, so the moral of the story is get used to the sigma notation even if it's scary at first. Because what we can do is putting together the summation notation with the idea that an infinite number of rectangles gives us exact area, we get the mathematical definition of the definite integral. So the definite integral of a function f of x on an interval a to b is the area between f of x and the x-axis on that interval. So we've been talking about area under a curve. That's all the definite integral is, but mathematically we can define it in terms of limits. So we're going to parse through all of this. I know it's a lot of boxes, but we're going to translate it all into words and explain it. So the integral with integral notation is this thing on the left. Okay, so we have integral and we have a sum. So I'm going to color that blue maybe. Okay, so we have two parts to this definition. One of them involves a limit and one of them does not. Okay, so now that we have that colored and we have it in two halves, this is our integral. This is our limit of a Riemann sum. And notice that we're going to have an infinite number of rectangles, but I'm going to talk about that. So let's start with the integral notation. So this thing is what we call integral notation. So it looks like a really skinny long S, and the bounds, so the interval a to b of the Riemann sum becomes the bounds. Okay, so we read this, the integral from a to b. So we read from bottom to top. And the smaller number always goes in the bottom. Okay, so then we have some function, f of x, is, okay, so now comes the tricky part. So I think the integral part of this is not so bad to read. The sum is what's hard to think about, but if you think about what we've done already, talked about chopping the thing up into little rectangles, it'll be okay. So actually what I want to do is start with the thing all the way at the end. So f of x sub I times delta x. This is literally our rectangles. So this is one rectangle, or actually the area of one rectangle. And that's height times width. So delta x is our constant width. So down here, constant width, or all rectangles have the same width. Okay, so that's it. That's our rectangles. Now what we wanted to do in our car problem earlier was we wanted to add up all these rectangles, and that's precisely what the summation does. So it tells us add up all the rectangles. But then how many rectangles do we want to use? Well, you should have seen in the exploring Riemann sums activity that the more rectangles you do, the more accurate your measurement. So it stands to reason if we take an infinite number of rectangles, which we can do, this is abstract math land, if we take an infinite number of rectangles, we should get an exact answer. So that's precisely what this limit does. So we use infinity rectangles. Okay, so that's what we're doing. So we're cutting it up in a bunch of little strips that are rectangular. We're finding the area of each one, we're adding them up, and then we're saying, okay, I want an infinite number of rectangles. So let the number of rectangles in go to infinity. All right. The last thing is just this x sub I. All this is saying is this is choosing a point within the rectangle's width. That's all that is. So we need an x value to be able to define the height. So that's why we need this sample point thing. Okay, so that is the limit definition of an integral. Now, you're not going to really be expected to do much with solving the definition itself. There might be one problem in your homework, but that's it. The more important thing is we're going to look at just translating between the two sides of the definition. Okay? So let's finally jump into some examples. We're going to start by doing a very visual example. We're going to estimate the value of the integral from 0 to 2 of x over x plus 1 dx. Oh, that's what I forgot in the definition. Okay, this is really important. So when we write dx next to f of x, that kind of relates to the delta x on the other side. So that way we have like a height and a width on both sides. Okay, so that's why this dx is here. And it basically just tells you which variable you need to integrate with respect to. So kind of like in our derivative notation, dy dx. Okay, so we want to think about this. That notation told us take the derivative in terms of x. And so dx tells us take the integral in terms of x. Okay, so let's make a note of that. Okay, so we want to estimate the value of this integral using the midpoint rule with 4 subintervals. Okay, so it's not necessary to draw the entire graph. Some of your problems may want you to do that, but here we're going to practice doing it completely algebraically with minimal visualization. So first, we're going to draw sort of like a pseudo x-axis and figure out the midpoints of each of our subintervals. So when I say pseudo x-axis, all I'm saying is pretend like you have an x-axis and you're dividing it up into your subintervals. We don't want to graph the entire graph. We're just kind of giving us the x-axis to help us visualize. So I'm going to draw my x-axis from 0 to 2 because I have those endpoints. I have those bounds on my integral, so we're going to use those as our endpoints. Now I want 4 subintervals. So if I want to divide this thing into 4s, first I need to know what is the midpoint. Well, the midpoint is 1, and the midpoint of each of those is going to be 0.5 and 0.7, 1.5. And so another way we could do this is if you wanted to find the width of each interval. So remember we have that thing where delta x is equal to v minus a over n. So we could do 2 minus 0 over 4, and sure enough that gives us 1/2. And look at how far we went in each of these intervals. So like if I took one interval, the width of that interval was 1/2, right? And that's true for every single interval. Now, we wanted midpoints of these intervals. So I found my subintervals, but now I want to actually find the point within each subinterval that I could actually use to find the heights of my rectangles. So I'm going to find the midpoint of each subinterval. And so I'm going to do that in red just so you can tell the difference. So in between 0 and 0.5, we have 0.25 or 1/4. In between 0.5 and 1, I have 0.75. In between 1 and 1.5, I have 1.25. And in between 1.5 and 2, I have 1.75. Okay, so the points that I'm actually going to use to find the heights of my rectangles are those red points. Okay, so that brings us to step 2. So we want to figure out what the value of the function is at each of the midpoints. So these were the rectangle widths. Now we want to find the rectangle heights. So f in this case, so f of x is equal to x over x plus 1. So I want to find f, the value of f at each of those red points. So first I'm going to do f of 1/4, which is equal to 1/4 over 1/4 plus 1, and that's 1/4 times, let's see, 1 is 4/4, that's times 4/5 if we flip the fraction. So that's going to be 1/5. F of 3/4 is going to be 3/4 over 5, wait, no, 3/4, that's 7/4. So 3/4 over 7/4 is going to give us 3/7. F of 5/4 is going to give us 5/4 over 8/4, which is 5 over 8. And finally, f of, let's see, that would be 7/4, is going to give us 7/4 over 10/4. Oh, wait, hang on. I did something wrong here. Shoot. Okay, this is 9/4, my bad. And this is going to be 11/4. So we get 5 over 9 and 7 over 11. Okay, so those are our rectangle heights. Now finally we're going to find the area of each rectangle and add them all up. So let's write this as one big sum. So we have f of 1/4 times 1/2 plus f of 3/4 times 1/2 plus f of 5/4 times 1/2 plus f of 7/4 times 1/2. Now notice, because all of my widths of my rectangles are the same, I could actually just factor out the 1/2 and then add up all of my function values. That's probably what I'm going to do here. So I could rewrite this as 1/2 times f of 1/4 was 1/5, f of 3/4 was 3/7, f of 5/4 was 5/9, and finally we had 7 over 11. Okay, so now here's where it gets a little bit tricky. So just for the sake of time, I'm going to put these in the calculator real quick, but you should practice not using a calculator for your exam. So let's see, we have 1/5 plus 3/7 plus 5/9 plus 7 over 11 and divided by 2. So our area is approximately 0.910. Okay, so if I were to solve that integral, and we'll learn how to do that in the next few units, but if I were to solve that integral exactly, I should get something close to 0.910 when I'm done. Okay, so that's how to use midpoints. Now left and right endpoints, very similar, but the difference with left and right endpoints, you don't need to use the red numbers. You'd need to choose 4 of the 5 blue numbers, depending on if you want the right or the left endpoints. Okay, now let's talk a little bit about the limit definition again. So we're going to just work on translating back and forth. So our first example, we're going to express the limit as n goes to infinity of the sum from 1 to n of e to the xi over 1 plus xi as a definite integral on 0 to 1. Okay, so first of all, I know I'm going to need my integral notation, and my bounds come from my interval. So this interval gives me my bounds. Okay, next I need a function. So I'm going to have my function is the piece in here. So maybe I highlight that in yellow. And the only difference when I write it in the integral is I'm not going to have the i's on the x's anymore. So I'm going to have e to the x over 1 plus x, and that's it. Okay, so this matches up with the yellow. And finally, I can't forget to write that dx. So every integral, you need to make sure you have a dx after your function, or d whatever the variable is. Okay, so that's it. That's how we express that as a definite integral. Now let's go backwards and express the integral from 1 to 3 of the square root of 4 plus x squared dx is a limit of Riemann sums. So maybe I'll leave that other example up there just so we can see it. So the first thing I need is I need to write limit as n goes to infinity, and I know that I'm going to need this giant summation, and that's going to go from 1 to n. All right, now I want to write my function using x sub i's. So I'm going to have the square root of 4 plus x sub I squared. And finally, remember, I need that delta x. And delta x is going to come from our, oh boy, delta x. Where did that come from? Let's go back up to our definition. A plus, oh, right, okay. So delta x is, okay, let me rewind really quick. All right, so this is what we have so far. We have the limit as n goes to infinity of the sum from I equals 1 to n of the square root of 4 plus x sub I squared times delta x. Okay, now remember in our definition we had a couple of things. We had that delta x is b minus a over n, and we also had that x sub I is equal to a plus I times delta x. So we need to find both of these quantities as much as we can, plug them in, and then we'll have our limit. Okay, so b minus a, I have 3 is b, 1 is a, so I have 3 minus 1 over n, which is 2 over n. And now that I know that delta x is 2 over n, I know that x sub I is 1 plus 2i over n. So I can plug this stuff in, so I get the limit as n goes to infinity of the sum from I equals 1 to n of the square root of 4 plus 1 plus 2i over n squared times 2 over n. And that is my Riemann sum. So this would be my final answer. And this makes sense because now notice I only have n's floating around, which is nice because my limit is written in terms of n. And the only other variable I have is this I. So maybe I'll do that in a different color. So I also have I, but I is taken care of in the indexing of the sum. Okay? So once you have your answer only in terms of n's and i's, then you're done. Okay, so the last thing you need to do is just check your understanding. I know this is a lot to go over in one lesson, so if you have any questions, please let us know. And that is the end of lesson 18. So I should mention, this is the final unit, so you have made it to where you have 4 lessons left. Actually 3 now that you've done this one. So you should give yourself a pat on the back for that. That's a really good job. All right, that's the end of lesson 18.